My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and a very good morning to all those who are watching this program live from Canada. Hope you are well and safe from corona pandemic. So today, I'd like to welcome you all to our 118 International Physics webinar. And today is a very special day for our department. Today, I'd like to welcome you all through a joint session between the Department of Physics, Pabna, University of Science and Technology, and the Department of Physics, University of Ottawa. And we have with us here today Dr. Professor Ebrahim Karimi, sir, Canada Research Chair, University of Ottawa, Canada, and he has already connected with us. So I'd like to welcome our speaker. Sir, good morning and good evening to here. So thanks for accepting our invitation, sir. So we'd like to say thanks on the behalf of the Department of Physics, Pabna, University of Science and Technology, sir. So for those who are new, I'd like to inform that we have divided our webinar into three parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver his piece. And at the end, we have a discussion time. Anybody can join with us, and you can also ask questions by commenting. I think you have already come to know the title of this today's International Physics webinar. Title is the Structured Photons, Their Application in Quantum Photonics. And our speaker is Dr. Ebrahim Karimi, sir, Canada Research Chair, University of Ottawa, Canada. And Professor Ebrahim Karimi received his diploma in mathematics and physics from Iqbal Lahori in 1997. He fell in love with physics and mathematics as a high school student while attending several national physics conferences. He received a BSc in physics with emphasis in mathematics from Karman University 2001. He joined the mathematics physics group in IAS BS for the graduate study and was ranked 18th among all the incoming students. He later changed his research focus and graduated under supervision of Professor Arshad Min Nahal, laser cooling and trapping of natural atoms. In 2002, Professor Yusuf Sabuti was his graduate advisor. During that time, he also worked on singular optics with Professor Mohammad Taghi, Tafil Soli, and Professor Hamid Reza. In 2009, he received PhD degree from the University of Naples under supervision of Professor Lorenzo Marucci Santamato. He received the Best PhD Thesis Award for his thesis titled Light Orbital Angular Momentum and its Application on the Classical and Quantum Information. After his PhD, he worked as a postdoctoral fellow, first in group of Professor Lorenzo and Professor Enrico in Naples, and later on Professor Robert Byrd's Quantum Optics Group. At the moment, he is the leader of Structured Quantum Optics Group at the University of Ottawa. So, Dr. Ebrahim Karimi, Canada Research Chair, is Structured Light, is trying to extend their limits. Karimi and his research team are designing and making novel optics and plasmonic devices that can structure single photons and optical beams. Plasmonic is the study of how light and matter interact. Since these devices can hold limitless amount of information, they have the potential to offer solution to the capacity limitation of conventional transmission techniques. By developing these devices, Karimi's research will lead to more efficient and compact way to capture light for applications such as quantum computation, quantum information, nanosensing, and super dense coding. Ultimately, these devices could open the door to developing ultra-secure communication schemes and ways of transmitting sensitive messages rapidly across the globe. So you can see his Google Scholar ID, and you can see his citation number is more than 7,549. And you can see his research gate, and his point is 47.45. So thanks for all of your patience. And now chance to go to our speaker, sir. I'd like to welcome you again. It's your time, sir. You can start your session, sir.
So, first of all, thank you very much, Professor Kumar, for the invitation. It's a great pleasure to be talking to your department and your audience. And many thanks also for the kind introduction. Thank you. So the only things that I want to say is that University of Naples or Napoli is the place that Maradona played soccer. Yeah. So Without further ado, I will go to the presentation. So I will share my screen, and I think you should have the screen share. No, okay. All right.
Yeah, we can see.
Okay, excellent. So, as you kindly mentioned, my expertise is structured quantum waves, or the way that we can shape waves and in general quantum particles, a quantum wave packet. And here I will explicitly just talk about photons. There is another direction of research that my team is taking and working on, which is structured electron beams. So at the moment, I only focus on structured photons, and we will have a short overview, and later on we will go slowly to, let's say, very recent activities that my group does. So when we talk about light, it is impossible to explain without Maxwell equations. So Maxwell equations unify electric and magnetic field and explain to the people that light or electromagnetic waves, they are coupled to each other. I mean, electric field and magnetic field are coupled to each other, and when you go to the free space, when you have no charge and you deal with vacuum, for example, then what you have some sort of wave equations, and those wave equations will tell people that electric and magnetic field they are in phase and they are oscillating in free space. And what you will see that, for example, in a easy form, they have some sort of plane wave structure. So, and when we are talking about the plane waves, I think most of us, we have seen that the electric field and the magnetic field, which they are orthogonal to each other, they propagate in a certain direction, and we know very well that the plane wave is a good solution, but is not a physical one, because essentially you do have the power is not normalized to 1. So this is something that we learn in undergraduate, and those people that they work in optics and photonics, they know further. So just to jump from the classical perspective to the quantum perspective and seeing what's going on between the two, I would say that when we talk about the light, we have 4 different degrees of freedom. So one is talking about linear momentum of the light, which direction the light is propagating, and that degrees of freedom, degree of freedom, when we want to watch it in the quantum perspective, is continuous space. So essentially, it changes from 0 to any direction if you choose it, from positive to negative. And the other degree of freedom that we do have is polarization of light, which is associated to the vectorial nature of the light, how electric and magnetic field and the direction of the electric field, traditionally, if you want to watch it, how the direction of the electric field is oscillating upon the time and in space. We know very well that light is transfer, and this is dictated by Maxwell equation. So the vector of electric field has only 2 different degrees of freedom. Is bidimensional. So it can be either H and V, or it can be left-handed and right-handed. So polarization space in the quantum language is bidimensional. It cannot take more than 2 values, 2 vectors. And Z superposition. On the top of these, also, we do have a phase of the light. So we can do the quantization in the transverse direction, and what we it seems that okay, there is a problem, and we can quantize the phase, and since most of the optics in laboratory and research labs, they have cylindrical symmetry, the most elegant way is quantizing it in the cylindrical coordinate. When you do the quantization in the cylindrical coordinate, then associated to the phi direction, you have a certain quantization which they call it orbital angular momentum, or what we call it integer value, azimuthal integer value. And this azimuthal integer value will tell you how the phase upon azimuthal direction will change, and that can take only integer quantities, but it can take infinite values. So it can be any integer number. The Hilbert space associated to this is infinite dimension but discrete quantity. And I would say during last decade, also people, including myself and one of my colleagues and my supervisor at that time, we got interested in how the intensity and phase of light is distributed along radial direction. And we tried to formulate this and find out how the algebraic approach to the radial direction can give further insight into these degrees of freedom. So those all are what we call it freedom that you do have it for the light, and you can use them to implement quantum information. So let's go further into two of those quantities, which is polarization. So essentially, as I say, that we can, since the light is transverse, we can have only two vectors associated to electric field and magnetic field as well. And traditionally, we look only at the electric field, and the way that the electric field changes upon propagation, either can go clockwise or counterclockwise. If you look at the single photon regime, you will see that for the way that the electric field is changing to be clockwise or counterclockwise upon propagation, you can have you can assign a spin angular momentum to the photon, and this spin angular momentum has a value of either +1 or -1 in units of h bar. So it tells you that either this angular momentum is along propagation direction or opposite to propagation direction. And this is somehow linked to the polarization of the light in a naive way. So if I want to tell in a naive picture, left-handed and right-handed superposition, they have spin angular momentum of +h bar and -h bar per photon. So talking about the azimuthal phase that we described, so essentially, since the beam should be physical, and this phase is essentially given by exponential of IL phi, which phi is azimuthal coordinate. If you change phi from 0 to 2 pi, then you should see exactly the same physics. So that indicates that L should be an integer quantity. And if you do a little bit of mathematics, you understand that this is assigned to orbital angular momentum of the light, and for a single photon that can take any quanta of h bar. So essentially, is L h bar per photon, which L can be an integer quantity. You can go from +1000 to -1000 or any other values that your system allows you and fabrication limit. For those people that are more familiar with these beams, we call also those beams singular beams, or beams that carry a phase singularity. And essentially, the singularity comes from the fact that azimuthal angle phi is undefined at the origin. So when you go to the origin, r equal to 0 or rho equal to 0, there we have no idea about phi. This is the singularity that cylindrical coordinate has with itself. And the same story happens for the beams that carry orbital momentum. If you go to the axis on propagation axis, there the phase is undefined. And since the phase is undefined, you expect to see no photon there. So essentially, the probability of finding photon there is 0. Or if you talk about electric and magnetic field, you can say that there will be no light there. So that's the reason that you will see a hole for the case then when L is not equal to 0. So when L is equal to 1, 2, or 3, what you will see, you will see a singularity there. And that singularity is really mathematical singularity, so you do have no dimension for that. And this is one of the reasons and one idea behind the invention and the technique that Stefan Hall developed to increase resolution of a microscope. So a good example of these, which usually I want to make a joke about, that is pasta fusilli. So pasta fusilli also has this structure, which were what we call it helical phase forms. So if we want to compare spin angular momentum, which is polarization, degrees of freedom of light, and orbital momentum, which is associated with the phase front of the light, then there are different ways to create them. So the easy way is for spin angular momentum is using what we call them wave plates, which they are birefringent plate, which allows you to control the relative phase between the two components of the electric field. So it can be decomposed in two ways, and then you will have different phase and group velocity for the light, and then you can, by adjusting and designing the proper way, you can control and create different polarization states. For orbital momentum, you have to control the phase front, and in order to control the phase front, you can do it with a different thickness of material. So now, what you want to do, you want to create a phase front which is helical structure. So then you have to have a glass or a material which is transparent and has a different thickness. And the thickness, as you see, is look like a staircase. So when the light is passing through the thin part, it exits from the material earlier. When it goes to the thick part, it exits later. So with this technique, what you can do, you can imprint the phase front that you wanted onto the beam. And as you see, there is a jump between let's say the staircase or the jump that you have in the staircase, and this jump should be in order of the wavelength. So that requires really precise nanofabrication. So if we want to look at the interaction of a beam that carries spin angular momentum and beam that carries orbital momentum, there are two examples that I've taken from my colleagues Jonathan Leach and Kishan Dolakia's group. So when on the right side movie, what they have two beams carrying spin angular momentum. One of them is left-handed, the other one is right-handed. They illuminate two microspheres, and with these two microspheres, they induce different rotations. So one of them is clockwise, the other one is counterclockwise, and with this technique, they can create a pump. So while for the beam that carries orbital momentum, if you interact it with particles which they are smaller than beam size, what they induce some sort of rotations which has orbital motion. So if I want to tell you again in a simple and naive perspective, spin angular momentum will cause a rotation around the particle axis, while orbital momentum causes a rotation around the beam axis. So you do have these two different notions for spin and orbital momentum, even in the case of electromagnetic field. So if I want to introduce structural light in one slide, I would say to you that light has, as we discussed, has different degrees of freedom. One, as we say, is the phase front, L, in the Cartesian coordinate. P is the radial part. N is the number of the photon that you can add it, which in the quantum optics perspective, the photon statistics is extremely important. And it is another way that people, they can control the structural light. And you can control the polarization of the beam, and also you can control the frequency, or essentially the time being. So when we talk about structural light, we are essentially talking about a wave function for a photon, which this wave function, I'm using this word for photon because that's never really less nice. So which you can control all of those degrees of freedom. You can have a coherent or incoherent superposition of different states. So essentially, as an example, on the right side, what you will see an example of the structured light or structured photons, which is a coherent superposition of different P, different L values, and different polarization states. And when you do the coherent superposition of these, you will get to a rich topology, which the polarization is not uniform, but point by point around across the transverse plane changes, and you will see in some region is a linear polarization, some region is circular polarization, in some region is elliptical polarization, maybe different-handedness. And also the probability distribution or the intensity profile of the beam also is changing in radial or maybe also in azimuthal direction. We could go also with a different way. So we call these in general structured light. And in quantum regime, we can call this structured photon. So we can create a single photon which is in this state, or we can create a classical light or a beam of light which has this property. Good. So I said briefly about elliptical polarization and circular polarization. Just we want to review. So when we talk about polarization of light, that is true that we have two different degrees of freedom, two vectors. So essentially two independent vectors. We can go with H and V, or you can go with left-handed and right-handed. And essentially, since this is a two-dimensional vector space, you can map it on a unit, a sphere with a radius of 1, and then you can work with an algebraic approach, and you will see that there is a mapping from SU2 group to SO3, and this mapping will allow you to have a visual picture of what's going on with the polarization, which is a two-dimensional vector. And in this picture, you will see the left-handed and right-handed polarization. They are on the north and south pole. When you go to the equator, you will deal with the equal superposition of these two. So, and then you will end up with linear polarization. And when you go on different points on the equator, you will see that this linear polarization only changes the direction. So it goes from H to anti-diagonal and then goes to V and any orientations that you may have. Any other points on the sphere, you do have elliptical polarization. So when we talk about elliptical polarization, it means that you have an ellipse. And for an ellipse, you have a major and minor axis and an orientation for the ellipse. On the top of this, you can look at the vector of the electric field, which is oscillating upon the time. and you have a certain oscillation direction. So you go either clockwise or counterclockwise. And if we look at the big picture, we will see that all of those major minor axes and also the orientation for the electric field and the direction of the electric field, which changes upon the time, and the orientation of the polarization ellipse, all is well defined for elliptically polarized light beam. However, when you go to linear polarization, we have no clue how the electric field is oscillating. It can go in both directions. So we call these a singularity which is assigned to the way that electric field is oscillating. We have no clue about that. For the case of left-handed polarization and right-handed polarization, also we have a singularity, and this singularity is assigned to the major and minor axis of the electric field. So, minor and major axis of the polarization ellipse, and in that case, we have no clue which one is the minor axis and which one is the major axis. So again, we have a singularity. These two singularities, they are not physical singularity. In this sense, we have lack of knowledge about the ellipse of the polarization of the light, and we are not expecting some physical quantity to be disappeared here, like phase singularity. So, for example, phase singularity was different because there we had no clue about the phase. Then, as a consequence, we expect that there will be no light there. Here, no, there will be a probability of detecting photon or having light there. But what is happening from the mathematical perspective, we have lack of knowledge about certain perspective and certain values of polarization. Description of polarization of light. So good, and if we look at the one of those topologies, which is people they name, I think John Nye, and John Nye named it, and after that I think Michael Berry as well. So they call this topology lemon, and as you see at the center we have a polarization. So for that point, as I say, we have no clue about minor and major axis of the polarization. Then we call this point C point or polarization point. And around this, you will see a line, which that line you have linear polarization, and we call this L-line singularity. Good. So singularities for polarization can be classified in three major quantities or major topologies, which is lemon, star, and Mons-star. And you can see that how this topology is induced. So you can look at the polarization axis for the lemon, and you do a full rotation, and you will see that when you look at the major axis, and if you do a full rotation and come back to the same place, the orientation has changed. So we call these +1 topology. While for the star, if you follow the same strategy that I mentioned, you will see that again, the orientation will flip, but the way that these vector is changing, or the major axis, the way that major axis evolves is changing, it will be opposite to the direction that you change. And then we call these -1/2 topology. And for the Mons-star also is +1/2 topology. So we can assign also topological structure to the polarization degrees of freedom. And there are ways that they can create them in a laboratory. One way that we develop is using liquid crystal technology. So we have laboratory where we can coat the glass, and we can align point by point the polymer on the surface of the glass, and we can glue them together, and then we can put liquid crystal, inject liquid crystal between the two glasses, and finally, what we will get when we shine the light on the top of these, we can manipulate intensity, we can manipulate polarization, and also phase front of the beam. So there are few examples how these slap, or let's say 4 micron thickness of glass can be used to control polarization intensity and phase of an optical beam. Also we can create very high topological charges, a beam of light which carries orbital momentum with high topological charges. And the technique, the principle that is behind of this technology is Panchart-Memberi phase. So the way that the geometrical phase can be used to induce certain phase and polarization structure. One question that we had in the past was how, when you take these, let's say, partial beam or the beam that is transverse, how when you take this beam, if you do tight focusing, how the beam will change, because in the case of tight focusing, the beam is not anymore transverse. So when you have a ray tracing picture, you will see the beam is focused in a certain direction. Then you expect that you have a component of the electric field along propagation direction. So we took one of those beams, which is a star, one of those topologies, and we did tight focusing. And with the technique that my colleagues, they developed in Max Planck, Peter Benzer in the group of Herr Loix, they developed, we were able to reconstruct polarization of light along X direction, along Y direction, and also along Z direction. And then we could look at the component of the electric field and their relative phases. And when we plot them all together, what we ended up with a three-dimensional topology, which, if you look at the major axis of the polarization ellipse, the polarization ellipse in this case is not anymore in the transverse plane. It has a Z component, so it becomes a three-dimensional object. And then along a certain radius at the focus, if you follow, you will see that they form a Mobius. So this was a puzzle for the community, and people, they were looking for this for many years to see what we call it polarization Mobius. Remember that these polarization Mobius is assigned to the major axis of polarization ellipse. So essentially, there is a field continuity. So electric field, as I showed in the previous slide, electric field is oscillating, and there is no discontinuity in the electric field in the transverse plane. What is happening, if you look at the major axis, you will follow them, you will see that the major axis has a flip. And if you look at the projection of these, again, you will see the star topology. This is what you started with. And this polarization Mobius exists not only at a certain radius, but almost in the entire the transverse plane. So you can change the radius and still you will see the Mobius. So when we started with these, then one of my students said, okay, why we can create three-dimensional topologies, why not creating knots? So so he started to design certain polarization topologies, which at the if we look at that polarization topology, the color coding will tell you what is the orientation of major axis of the polarization ellipse. So you will see 6 singularities, 3 at the center, which at that 3 points, what you have lemon topology, and you have 3 other points which you do have a star topology, which they are located at those regions. So one of them has a +1/2 topology, the other has one -1/2 topology. And if you look at this beam and propagating them along certain direction, you will have a dynamic for those point of singularities. And if you follow them, you will see that they will create from a given plane, and then they evolve, and finally they annihilate. And if you follow all of those trajectories, you will end up with a form of a knot. And this example will give you a trefoil knot, which you can see the theory and experiment. And the surface will, the shaded area will show to you the cipher surface, which the cipher surface is the way that you can characterize a knot, or you can characterize certain topological structures. And there are few examples, and I think those are associated. In one case, it's to trefoil, the other one is associated to figure 8 knot. So we could create Mobius at the focus, and also we can create knot. And another valuable question that my student had: why not mixing these two together? So assigning a frame knot, and that was a collaboration that we started. I think the knot topology was a collaboration with Mark Dennis' team in Bristol. And then when we started to look at the frame knot, then we started to do a collaboration with Eliyahu Cohen and Avishai Karimi in Israel. And we find a mathematical way that they can assign frame to a knot and can use them for communication. So so far we only talk about how we can have curiosity about the structure beam, and how can we assign mathematical tools to them, and how we can see that the beam is evolving. Here, what we have done, we have taken one of those frame knots, and we use them as a backdoor to establish a communication, which is based on the prime factorization, and something like RSA protocol, that they can use it to establish a secure communication. But this is still classical communication. So with this example, I'm jumping to one of the application of structured light in high-dimensional quantum communication. How many minutes do I have?
Okay, we have about half an hour.
Half an hour. Okay, excellent. So so far, is there any questions? Or
we have one question, so we can. I think we can ask it at a discussion session. Maybe it will be better.
Okay. Excellent. So now we will discuss about high-dimensional quantum communication. First, when we talk about quantum communication, and in general communication, you have 2 points, minimum number. You have Alice. Traditionally, we use Alice and Bob. Sends message to Bob, and Alice, what she does, she picks up a way that she wants to do the communication. Either she wants to use light, or she wants to use electric field, or she wants to use smoke, whatever, to send a signal. And when she chooses the carrier, then she wants to understand how she can create them. She can manipulate that, let's say, message, and how she can transmit them. On the other side, Bob wants to know the technique, how to detect them, how to get the information, what we call it, having the detection system and having detector system, and finally doing some sort of, let's say, classical error correction and privacy amplification, and etc. So usually we would prefer to use photon. In the past, people, they use electrons, so the old-fashioned cables, phone, wire phone. So what people they use at that time was electric field, essentially, or electrons, the current. And now we use photon. Why? Because photon, the technology that we have for photons is much faster, and a photon rarely interacts with materials. Of course, we have diffraction, we have reflection, etc. refraction and many other things, but is much less than the electron, because electron has a charge and essentially interacts with everything around us. So, when we talk about quantum communication, we are talking about this. So, techniques, degrees of freedom, the channel, the protocol, the way that you detect them, and detectors and classical amplification, etc. And in general, in the quantum language, Eve has access to everything in this system. It can send a signal to your laboratory. It can send signals to Ali's laboratory. It can interrupt the link and many, many other things. So anything apart from these two is considered as Eve. So and remember that Eve's action in the quantum communication will be inducing noises. So usually I have an example, and this example is that in the old-fashioned communication system, we had a phone which was connected to a wire, and usually it happens in a house that we had two phones. So sometimes happens that another person at the home picked up the phone and was listening to a communication between two people. So the action and the action of the person and which picks up the phone, the second phone, or let's say the third phone, was inducing a little bit of the noise in the channel. So here is the same story. What we do, we reduce the signal so low that any noise that will be interrupting the channel can be detected. And this is the way that quantum communication works. I mean, revealing the action of what we call it eavesdropper. So since we are talking about high dimensional and high dimensional and using structured light, let's go and look at the feature of this. Assuming that I'm going to send letter M, okay? If you go with ASCII code, letter M in the 32 bits computer is given by 0, 1, 0, 0, 1, 1, 0, 1. And we know that we work in binary. Why? Because our transistors, diodes, they are working based on and off. So they are digitals. So in order to send letter M, what I have to send 8 signals. And for each of those signals, I have to clarify if the message is 1 or 0. And when I'm sending this signal, any of those 8 packets, and let's say the wave package or wave package which has one of those 8 signals, if any of those is missed, then I have to resend the message again. So working in a binary has a drawback. The drawback is that essentially you have to translate anything in a binary language. So it means that the number of, let's say, signals that you have to send, the way that you create them and the number that you send and the number that you detect them is really huge. Why we do have this drawback? Because everything in our computer is based on 0 and 1. However, what we can do, we can work with higher alphabet. So we not necessarily work with a binary scheme. You can work with the 0 and 255. And if you work with 0 to 255, then each of those, let's say, I'm picking up the helical structure. Each of those helical structure will be assigned to certain quantities. For example, in order to send letter M, I have to send one photon with specific, let's say, helical structure, or with a specific structure that has. And I know that all of those, let's say, helical structures, they are orthogonal to each other. So we have access to more alphabet. And if I want to just tell you, so if you want to send a classical message, which is given by these, I think it's 30 or 30, let's say, digits, If you work in the base of 4, you will see that this length of string reduces really lower. And if you work in the base of 7, it reduces further. If you work in base on 10, you will see that it reduces much more. So essentially, in the classical perspective, going with a higher alphabet has a benefit, which the benefit is that you can send more signal in a single carrier. And on the other side, also we know that is more green because you spend less energy on generating, sending, and detecting. However, in quantum regime, we have something more. We have qubits. So we know very well that qubits is deal with two-dimensional space. But we know that the product of two qubits will never be a q quartz. So, this will tell us that if you go to higher dimensions, we in the quantum regime we will have access to higher dimensional space, Hilbert space, which this higher dimensional space, Hilbert space, has properties which you don't have it in the lower dimensions. And the example was the product of two qubits will never be a q quartz. Good. So with this introduction, now let's introduce the quantum cryptography. In quantum cryptography, there are when we talk about quantum communication, we have different ways to do send messages using the quantum technology. And those techniques, they are based on several facts that you do have it in quantum mechanics. One of them is that in the quantum mechanics, in the quantum mechanics, we don't have definite reality. So everything everything can be, for example, we can have superposition states, and prior to the measurement, we have no clue about the state. So you are in superposition. There are two probabilities, or even three probabilities, or several other probabilities. So prior to the measurement, there is no definite reality. So we cannot really assign a reality to a quantum system. Any measurement in the quantum language has a limit. So measurement, when I say measurement about conjugate quantities. So for example, we cannot measure X and P at the same time. We cannot measure, for example, energy and time at the same time. So all these conjugate quantities, they have a limit on measuring them. And the last one, which is a consequence of the second, the uncertainty principle, is cloning. So we, in quantum world, we cannot do cloning. There is no cloning theorem, which tells us that if you have an atom to copy a quantum system, to make a copy of a quantum system, these copies, they will be imperfect. So they have some, let's say, errors in them, which they will be introduced. And this is a consequence of uncertainty principle. However, there is optimal cloning, which will tell us that how can we go and saturate the uncertainty principle. So just to tell you an example, let's assume that I have a quantum system. I can make a copy of this. For the first system which I have, and I make this copy, so now I end up with two copies of the same quantum system. For the first one, I can measure X. For the second one, I can measure P. So then I can violate uncertainty principle. This is I would say the physics behind of this. So you cannot make a perfect copy of a quantum system. Good. Now look at the high dimensional key distribution, and this is as I say that I'm not talking about all quantum communication techniques. I'm looking only at the quantum key distribution, which is one of the techniques that they use for quantum communication. And I'm looking at the high dimension. And it was very clear from the classical perspective that even in a high dimensional classical communication, you can increase the channel capacity, you can send more messages, but also we want to check it in the quantum direction. If you go with the high dimensional quantum key distribution, what you will get as a benefit. So this is on the right side, you will see a curve. And this curve will tell you what is the secret key rate and will versus quantum bit error rate. The quantum bit error rate is what I told you at the beginning, is assigned to the presence of Eve. So if someone wants to interrupt the communication channel, we need to use noises. So by monitoring the noise and putting a threshold on the noise, we can guarantee the security of quantum communication channel that we do have. So if you go with only 2 alphabet, we can send at the zero error, we can send 1 bit of information. If you go with 4 dimension, we can send 2 bits of information. If you go with 16 dimension, we can send 4 bits of information. However, if you have an error in the system, which in general we assign any error to Eve, then you will see that the secret key rate also follows the same strategy. So higher dimension have a higher secret key rates, but also the threshold which you reach to 0 key, which tells you that you cannot establish a positive key, also this threshold has increased. So for higher dimensions, there are more noise tolerance. So there is an additional benefit in the quantum regime to use high dimensionality. So I'm giving you an example that one of my students did. So he tried to do an optimal cloning attack to a secure channel. So what he did, he built up an optimal quantum cloning machine. Remember that cloning is forbidden, but we can ask what is the optimal one. So he tried to make 2 copies. And then as a consequence, you will see that if you attack to a system by cloning, then you will bring those matrices that are projection states. By the way, I have to first go with that. So Alice generate a state and then send it to Bob, and Bob has to freedom to choose either being in the Fourier transform space or in the same space, and measuring them. And when you do the cloning attack, what you will see that the certainty in detecting them when they are in the right base has been affected. And this is dictated by optimal cloning scenario. So you will see that in the dimension 2, in dimension 3, 4, 5, and 6, and 7, the cloning attack will induce noises. And these noise, you will see, is higher than the noise threshold that I introduced in the first slide. So they can be easily detected by Alice and Bob. So this is a proof for those people that they are interested in high dimensional quantum key distribution. That going to higher dimensions will give you will provide you the way that you can make your channel more secure. So people, they have taken optics out of the laboratory, and they tried to build up a secure channel between 2 buildings at the University of Ottawa. This was in collaboration with Max Planck Institute in Erlangen in Germany. And what they have done, they use 4-dimensional space, and they try to send messages there. And what they got, they want to compare 2 dimensions versus 4 dimension. In the case of 2 dimensions, they were able to send 0.43 bits per carrier. And in the case of 4 dimensions, they were able to send 0.65 bits per carrier. And in one case, what we had, we had about 11% error, which we were not able to use the two-dimensional space. Then we used the four-dimensional space, which the threshold for establishing a secret key was almost 19%. So that gives the benefit of using high-dimensional space. And during last 2 years, they built up two, let's say, sheds and laboratory on the roof of one roof in the laboratory of in library of NRC, National Research Council, and another one at the University of Ottawa. And what they have tried to do, they try to send messages there. So you can see it on the Google Earth now that the distance between these two is about 5.4 kilometers, and now you should be able to see them even from satellite. So this is Alice, which sends it generates the state and sends it to Bob. And Bob's laboratory is located in on the roof of one building at the University of Ottawa. And we are trying to develop the third point in such a way that we have Alice, Bob, and Charlie, and we may created a quantum network. But everything is almost done due to the pandemic for more than a year, essentially. And this is Bob's laboratory at the front of our building, which the other laboratories of my group is located. And what we do have also, we have scintillometer, which we can look at the turbulence, and we can characterize the turbulence. And also we have adaptive optic system, which is a supercomputer, which can compensate for the turbulence and reducing the effect of turbulence, and by using a target beam. So I do want to talk about the turbulence and the way that we characterize. I think this will be almost the last science part. So also people, they try to use it for underwater communication. So water is almost opaque for most of the wavelengths. So essentially, you will see that at infrared, light can penetrate only for a couple of 100 micrometer. If you go to, let's say, 800 nanometer, can penetrate up to 2 meters. If you go to 532, it can go to 75, and finally, if you go to 400 nanometers, you can go even to 230 meters. So, and after, again, if you go shorter, you will see that the water also it will be opaque to those wavelengths. So it's extremely difficult to do communication with an object which is underwater, because almost all wavelengths will be absorbed by water, apart from green and blue. So people from my team, again, they brought equipment out of laboratory. First, they tried to do it in a swimming pool in one of my students' parents' house. And there they tried to do quantum communication through underwater channel. Underwater channel was very strange because we have seen very strong turbulence there. And the turbulence were extremely different from free space. And this is an example just to show to you that if you send even a laser beam, what you will see, that you will see astigmatism, strong astigmatism through underwater. This is coming from the fact that you have eddy currents close to the surface of water or inside of the water, even going down below the surface. And also 2 years ago, they went outside of laboratory. They went to Ottawa River. They found a cottage. They tried to do communication there, and they were able to reach to 5 meters. They were unlucky because there were huge rains and the water was dirty. We had a lot of algae and etc. So that causes the problem because when you work with single photon regime, you have to be extremely precise. And losses was so huge that we couldn't do anything more than 5 meters. And also there they characterize the turbulence. They look at how the turbulence will be affecting the system, and you will see that if you look at this Zernike polynomial, which tells you how the turbulence is strong, we don't have a tip tilt, which usually people that they work in middle turbulence, middle range turbulence, they will see only tip tilt. They see much stronger, which is a astigmatism way, and the way that beam changes the profile. And this causes also singularity splitting when you go with the classical communication. And that puts limits, and we could even go to higher than dimension 3, and everything was limited to those. And going to higher than dimension 3, you need to develop an adaptive optic system that compensates for the turbulence that you have in this in the channel. And last year, they went to a flume in a National Research Council, and they were able to extend the range to 30 meters, and they did a characterization by changing the communication length. And this is a setup just to show you and having an idea about the way that people they do this characterization. And this is one of my students, Alicia Seat, which she sends blue and green light, and you will see that green is the penetration due to the green is much shorter because it is absorbed by water. And they were able to go to 30 meters, and they could have about 8 kilobits per second. And the closing slide is that I strongly believe that we need to do communication, not necessarily classical, but not necessarily quantum, but even classical, through, let's say, curved space-time. So people, they may go out of, let's say, a solar system, and then they want to do communication with Earth, and at that time we can not neglect the relativistic effect and explicitly the curvature of the space-time. And this is the work of one of my research associates, which he looked into the way that wave packet will be affected by the curvature of space-time. And he looked at 2 different examples when the encryption is done on the longitudinal mode, and when the encryption is done in the transverse mode. And what he found that that is extremely affected, and even if you have a Gaussian profile, then or let's say Gaussian profile for the time being, then after that, after the certain propagation, you will see that this is shifted, and that goes to higher modes and induces crosstalk. This is important because when we deal with quantum communication, the crosstalk plays a significant role, and it should be considered. So this is a research development that we are trying to do also with other colleagues, and see if whether we can have any proposal that can be measured in the laboratory. So I'm closing. So the goal from my team, apart from having fun, of course, developing different techniques, developing novel way to manipulate light, and designing complex structure, and also understanding how it evolves and interacts with material, is developing, helping in development of Quantum Internet Canada with colleagues in Waterloo, Calgary, University of Toronto. And also with my European colleagues is developing a microscope that can use structured electron beams to get more information from materials. I would like to thank my team. This is work by a group of people, including most of the members of my team and also most collaborators all around the world. So I would like to thank all of them, and also funding agencies. I think I'm done.
Thank you, sir, for your wonderful presentation, sir. I think students have learned a lot of things about the traction photons and its applications in quantum photonics. So if you allow, sir, we can start our discussion session, sir. We have got some question in comment and in inbox also.
Mm-hmm.
So the first question is, what is quantum cryptography? We
I
have
think
already discussed.
that was earlier. Then I think more likely the description that I gave. So in quantum cryptography, as I described, we do communication. Let's say you and me, we want to have a secure channel. We share a key together. Okay, let me do something else. I think I have something. You do see my screen, right?
Yes, sir.
Okay. Okay. So we have Alice and Bob. They do communication together. We use the public channel. Can be internet, can be whatever. Okay. We share a message, and this message is in public. Everyone can have access to this message. This is the message that we do. Okay. It has no meaning essentially. What we do, we use a channel which is a secure channel, and this secure channel is used to share the key to decrypt the message. This is what we do. Right now, the most of the description and most of the key that is used is based on hard mathematical calculations. For example, if I want to be very naive, honestly, it's more than this. Is RSA protocol. You have to look or this or internet. You will find a lot of text about how the RSA works. But it looks like finding prime numbers. I mean, it's behind of this. So whenever you have the key, you can decrypt the text and you can get it. What we do in the quantum key distribution is using quantum mechanics to share the key. And using quantum mechanics to share the key is based on this principle. Okay? So Alice and Bob, they choose different bases. I call them red and blue. One of them is circle, the other one is cross. Circle and cross, they are conjugate quantities, like x and p. Okay? And we know that in quantum mechanics, you cannot measure x and p simultaneously. You can measure one, but you cannot measure the other one. And we know there is no cloning theorem. You cannot copy and then make two different measurements. So Alice randomly chooses one of those conjugate quantities, what we call the mutually unbiased bases, and encrypt one of the messages inside. So she picks up, let's say, circle base, sends, plus base, sends the message. We are not talking about the message, by the way, the 0, 1, and etc. Those are completely just for clarity. Alice assign a certain, let's say, quantity to them. What is important that Alice randomly picks up circle plus circle, whatever, with 50-50 chances. So she picks up any of those. And she sends to Bob. And Bob also randomly without communicating with Alice, picks up either circle or plus. So, for example, for the first one, he picks up plus, plus, circle, circle, plus, circle, circle, plus, circle, circle. Okay? Whenever Bob is in the right base, which means that he has the right base to measure, to do the measurement, to perform the measurement, he is sure that he will get the right information. So, for example, we see that among all of those, let's say, signals, only in 4 of them they are in the same base, on the same base. So after doing all of the measurement, Alice and Bob, they communicate to each other. They say, okay, for the first one, I use circle. Bob says, no, I use cross. They discard that. For the second one, Alice says that I use plus. Bob says yes. They don't talk what is inside of what was the message that Bob received. What they share only is the base. And finally, after that, they have a key. This is the quantum key distribution, which anyone that interrupts, I mean, Eve, when it interrupts, it induces some noises. And there is a limit that Eve, since Eve also has this probability of being 50% of the chances in the right or wrong basis, then also Eve has a limit in getting the information. And the presence of Eve, if Eve wants to do some attack, will be affecting the value of those measurements, which after the privacy amplification or error corrections can be figured out.
Okay, sir. Thank you. We have another question, sir. So, how can match a liquid crystal and its application? How can match liquid crystal and its application?
I did not get the question. How can we make the liquid crystal? What?
How can we make, maybe I don't know the exact question, but it's written like that. So how can made liquid crystal and it's maybe the application of liquid crystal, and how can we made liquid crystal? That may be the question.
So I say that look, liquid crystal can be used. I mean, right now, all of us, we are using liquid crystal. The screen of your computer is liquid crystal, is pneumatic liquid crystal. So if the person meant how we can use liquid crystal to structure light, this is what I said at the beginning. This is the way that we have a piece of glass, and this glass is ITO glass. It means that you can apply voltages, exactly look like what you have on your screen. And then point by point, we can write a polymer onto it. So we can align the polymer. And when you have 2 pieces of glass like this, and on 2 sides, you have a certain orientation for the polymer. When inject the liquid crystal inside, then the liquid crystal starts to orient itself between these 2, and based on the orientation of the polymer. So if the polymer one is oriented in this direction on one surface, and the other one is oriented orthogonal to that one, the liquid crystal follows these 2 orientation adiabatically. So when the light is passing through this, the polarization of light also will be affected by this system. So, for example, if you have the optical retardation between these 2 is a half wavelength or a full wavelength or a quarter wavelength, then you can change linear polarization either to linear polarization to circular polarization, and etc. However, what is important that since the orientation of these liquid crystal can change in transverse plane, then you can induce the geometrical phases to the beam. And this is the way that people can control polarization, phase, and also if you add a polarizer at the end, you can also control the intensity.
Thank you, sir. We have another question. So how can applied 3D polarization topology in classical mechanics?
Oh, Classical mechanics, I mean classical communications. I think that's the question. So this is an example that I mentioned. We do have trefoil. Okay, let me see if I have another in another presentation. I don't have in another presentation. No, I don't have it here as well. Okay, so just to tell you, so what is happening? Look at the frame knot. Okay, this frame knot has a mathematical representation. This mathematical representation, what we call it, braids. So you can decompose them in some sort of braids, which you can see it on with my cursor. This is the braid representation. This braid representation, you do have first of all, it's unique. So you can have if it's a three, let's say 3 strings, then it's 3 strings. But then you have a freedom on where you add the twist to them. Also, you have, since it's a frame knot, it's not only a knot, so it has orientation. Then you can have a twist there. So you can assign the twist there. And then for each frame, you can assign a prime number and certain quantities that you do have it as a freedom. This is what I describe as the protocol that we develop. Encode a large integer n in a prime number as follows: assign to each strand a prime number of pk. In each strand, the number of half twists, which is defined by this braid representation, it's given. Then choose a positive number, which you do have a freedom for that alpha to be shared with the receiver securely. Alpha and beta, they will be shared securely. And then you can, by the product of them, you can get the big integer number. So this is the way that we develop the technique, which is look like the RSA protocol for classical communication, but using the 3-dimensional polarization topologies. It's a bit complicated. Sorry, you can go to the paper and look at it.
Thank you, sir. This may be the last question. So, what is the quantum bit error?
Oh, quantum bit error rate. So you follow the quantum P distribution as we described. So after sifting, when Alice and Bob, they picked up, let's say, the right basis, then they have a string. So of 1, 1, 0, 0, 1, 0, whatever, maybe a string of 1,000. Then Alice and Bob, they sacrifice certain of those strings. For example, from 1,000, they pick up 100. And they share the value. They're supposed to not share the value. They only check the basis. They don't share the value. But what they do, out of these 1,000, let's say, sifted strings, they check only the content of 10%, which is 100 of them. And they say, okay, Ali says that for the first one, I have 0. Bob says 0, excellent. Ali says 1, Bob says 1, excellent. But it happens due to anything, due to errors, due to imperfections, but we assign everything to Eve, because Eve action will be inducing noises. Certain time happens that Ali says I have 1, but Bob says I have 0. Then they call this error in the system that happens. And they count the number of error. if the number of error in those bits after shifting is higher than 11% for the two-dimensional case, they say that this channel is unsecure. Okay, so quantum bit error rate is by comparison, comparing the outcome after the shifting and revealing those results between Alice and Bob. They will share that even publicly, okay, and even ear can listen to this communication, and we call these quantum bit error rates. The error that is in the shifted signal or shifted keys.
Thank you, sir, for your nice presentation and wonderful discussion session, sir. I think students have learned a lot of things, and it's a very, very good opportunity for them to interact the big scientists like you. So it's my honor and privilege to host you in my international physics webinar, sir. So thanks again, and hopefully in near future, after the COVID, we'll definitely invite you in my country for a face-to-face session if you have a time, sir. That will be a very wonderful session for us.
Thank you very much for the invitation, and of course, I mean, if anyone, I think you do have my email address. Is on the website as well, SQO website. Yeah. So if anyone has questions, I will be pleased to answer to them.
Yeah, thank you, sir.
Okay. Thank you.
Okay, as the video will remain in the YouTube and Facebook, I think anybody can ask question, and if we got question, I'll send to you, sir.
Absolutely. Thank you, sir. And have a wonderful weekend.
Yeah. Bye, sir. Good night.
Thank you. Bye-bye.
Have a nice day. Bye.